Okay, so let's continue with our problem. So I start the recording. All right. So we are given in this new space, we are given a set of lines, and our goal will be to compute the level for each intersection point in this line arrangement. For each of these vertices, our goal will be to compute the level. That's our goal. So we are going to first compute the doubly connected edge list and compute the levels. But before I continue with this problem, let's go another sidetrack and how this duality transform can help to see us the problem from a different perspective for a different problem. All right. Now, maybe I can do it at the end of the lecture. Yeah, let's do it at the end of, without breaking our flow. Let's do it at the end of the lecture for this other problem. Okay, now we're going to, we have talked about duality. The duality we have talked about is properties. It also has a geometric intuitive geometric interpretation, which is this. This is a special parabola. U is equal to x squared divided by y is equal to x squared divided by 2. So if your point is on this parabola, its dual transform is the tangent. It becomes the tangent line to this parabola at that point. So if your point is P here, for example, its dual transform will be this P star. And this, because as you can see, this x squared divided by y is equal to x squared divided by 2. It's, if you take the derivative, its slope is x. So the x coordinate of this one becomes the slope of the line, and its y coordinate becomes the intercept of the line. So it's actually it intersects the line at the negative y coordinate. So if your point is on the parabola, then the tangent at that point on the parabola becomes your dual line. If your point is not on the line, you just draw a vertical extension to intersect. For example, for this point Q, its dual transform is this Q star, and how it is found is described in this figure. It will have the same slope as since this Q has the same x coordinate as this P, which means that it will be a line that is parallel to P star. So they will have the same slope. And therefore, whatever, you just draw a vertical extension from this Q to this parabola, or if this Q was above, inside the parabola, you draw a vertical extension below. You find the point P that you intersect the parabola at that x coordinate. That becomes the slope of your line. And but the actual line is a little bit shifted, and the shifting of your line is equal to the distance of your point to the parabola, whatever the distance is. So for example, if you have a point here, let's call it point R, its dual line will be somewhere here, which is parallel to this P star and Q star. So this is just the geometric interpretation. You're not actually not interested in that, in this interpretation, only if you want to visualize how the dual lines will look for a given set of points. You may then consider this geometric interpretation. But other than that, the only thing that we're interested in for this problem will be that incidence and order preserving properties of this duality transform. Now we have turned our problem to a given set of lines as input. And what we will first do is compute the doubly connected edge list of these lines. We have an arrangement of lines, and this arrangement of lines induce a subdivision of the plane. We have faces, edges, and it's clear that the complexity of this subdivision is quadratic because there are ON square vertices. The number of faces and the number of edges are also ON square each. So this is the theorem. So this is the subdivision induced by an arrangement of a lines, an example subdivision. Just like a regular subdivision, we have faces, vertices, edges, and its complexity is quadratic with respect to the number of lines that induce this subspace. If we have n lines, an arrangement of n lines in the plane, the number of vertices is at most n choose 2. So this is, as you can see, this is n choose 2. Okay. n times n minus 1 divided by 2. And this will be equal to that if no lines are parallel to each other. Okay, if some lines are parallel to each other, it may be less than that. But at most, this is the largest it can be. The number of edges is also at most n squared. The number of faces is at most n squared divided by 2 plus n over 2 plus 1. So if you look at this, all of them are quadratic, which means that the entire complexity of the subdivision will be quadratic. Now, how do we build this? So that's the next thing. So this figure shows actually a way to build that. How do we also traverse the arrangement? If we have half edges, the vertices, we will be able to, given a doubly connected edgeless representation of this arrangement, we will be able to traverse it nicely by following, for example, you may start, look at this line that enters this arrangement. We can find which edge of this bounding box we enter. After we find this intersection, we can follow the edge records next until our line intersects with a different edge of the same face. It will tell us which face, which edge we're exiting this face. Now, after we find the face that the edge that we're exiting, we can take its twin. So from this edge, we jump to its twin. And after its twin, we again follow next pointers, next pointers until we find the following edge. So we can actually find the edges that we intersect, that this line intersect one by one by traversing the next and twin pointers. And the incident face of these twin edges will also indicate us that we intersect this face first, then this face, and then this face. We can find which faces of the arrangement a given line intersects with by following these edge pointers here, as you can see. Okay, so this is possible. The doubly connected edgeless helps us to traverse this arrangement of lines. So this is what we're going to do. With this traversal, actually, we are going to have an iterative algorithm, incremental algorithm. We will incrementally build the doubly connected edge list by inserting each of the lines one by one to an existing doubly connected edge list. And with this, we will build the final doubly connected edge list incrementally. First of all, we need to first define, for example, this bounding box. What is the part of the arrangement that concerns us, that we're interested in? First of all, we may want to see all of the vertices wherever these lines are intersecting. For example, there are no intersections beyond this bounding box. All the intersections between these, how many lines? 2 and 1, 2, 3. There are 5. Okay, so there are 5 lines here, right? If I'm not counting. Yeah, I think there are 5 lines here. So all the intersections between these 5 lines you see are actually contained in this bounding box. And there are O(n) square of those intersections. So the first step would be, for all of these O(n) square intersections, we can go over them, find the minimum x coordinate, maximum x coordinate, minimum y, maximum y. So in O(n) square time, by going over all of the vertices of this line arrangement, we can compute the boundary of this arrangement such that all of the vertices are going to be inside. So, okay, so we can do that. So in order to have all the vertices inside the bounding box, we compute the boundary, we find minimum, maximum coordinates of these vertices. This will give us a bounding box. So we will start, then our algorithm will start with an empty bounding box, no lines inside it, with 4 edges. We will have the doubly connected edge list of that bounding box only. Then for each line, we are going to process that line by finding which faces it affects. We are going to, so the line is going to start intersecting our bounding box through some edge. It will enter the bounding box and it will exit the bounding box. So during this, while it's piercing through the bounding box, which faces are affected? Each face that this line intersects with, it has to split into 2 faces. Okay, so each line splits a face that intersects with into two faces. The face records should be updated according to that. The intersection points on these edges, they become new vertex records in our doubly connected edge list. The half edge records, there was a big half edge here, now it's chopped up into two pieces at this intersection point. So actually it shows it nicely. So if you have a face like this, when a line enters here at this point, for example, what we have to do is we have to chop these two long half edges into two, insert two new half edges for the portion that the line is inside, and the face record is also split into two. So we need to update the face records only concerning the faces that face records, edge records, and vertex records are going to be updated for the parts where our line pierces through. Okay, so for example, certain faces here, for example, look at this part of the doubly connected edge list. This part of the doubly connected edge list is not affected at all by this line. Okay, so, and this face also, this face, these half edges, they're not affected. So when we are incrementally building our doubly connected edge list, we'll only find the faces that we intersect with and update them according to this figure here. Okay, now this brings us to this problem. Actually, let me maybe go over the slides to show these things. They're already drawn there too. The slides also give other examples of other transforms. So you can take a look at that too. Oh, by the way, this duality transform also tells us the convex hull, for example, becomes the envelope of given lines. So the convex hull trick can be used in this dual space. When you compute the convex hull of the transformation of these lines, it gives a certain envelope of these lines, a certain region where all of the lines are, all of the points are below them, something like that. Okay, so I'm going to skip this part. Yeah, here's the incremental algorithm that we are going to do, the refined incremental algorithm. So here, as our line pierces through this subdivision, we are going to determine which faces we intersect with, and then update those faces accordingly. Now, here is the important thing. So this zone theorem, actually, I think the book describes it better than this one. During this incremental process, the next thing will be that we'll be concerned is what is the complexity of this incremental algorithm. For example, a line pierces through the doubly connected edge list, and if the previous theorem told us that the complexity of the doubly connected edge list can be quadratic. So imagine you're in the middle of the algorithm where the doubly connected edge list is constructed for half of the lines, and over two lines, half of the lines are processed, and you have a doubly connected edge list, which contains ON square faces, ON square vertices, and ON square edges. Now, when you're going to insert a new line into this quadratic size doubly connected edge list, what is the time that you require to update the face records and edge records that are affected by this new line? It seems that in the worst case, it could be n squared because the complexity is ON square, right? There are ON square faces here. Can a line intersect with ON square faces? Or can it affect ON square edges? Can it introduce ON square new vertices? It cannot introduce ON square vertices, that's for sure, because I mean it will intersect with n minus 1. If this is the ith line that we are processing, it will intersect with I minus 1 previous lines at most, okay? We know that the number of vertices that are going to be introduced are going to be linear. But what about the faces? Can it affect quadratic number of faces? Luckily, this part, the zone theorem tells us that this is not the case, okay? It's here. So the zone, let's first define what a zone is. The zone of a line is the union of faces, edges that it affects. So this is actually the zone of a line is the complexity of that intermediate step in the incremental algorithm when we are inserting a new line. And without loss of generality, we can assume that this line is the same as the x-axis. Okay, so when you insert a line which is parallel to the x-axis to this one, this is what the proof uses actually. But for any line, this zone is the zone of the line is the all these union of regions, faces, edges, vertices that the line interacts with or is going to affect. This is the part of the doubly connected edge list where we need to modify. Now, the zone theorem tells us that this is linear. The complexity of a zone of a line in an arrangement of m lines. If you have m lines, although the doubly connected edge list, the subdivision, is quadratic in complexity, the zone of another line that passed through this subdivision is linear. Okay, so this is the main reason we have this theorem in this part of the book is to show us that we can construct an arrangement of lines in O(n) squared time in total. Because in order to insert every one of those lines, we are going to spend linear time. In linear time, a single line can be inserted into an existing doubly connected edge list. And since you do this for every one of those lines, and you have n lines in total, so the zone theorem is used to show that the computational complexity of constructing the final arrangement is O(n) squared. All right, so this is what the zone theorem is about, to tell us that it's not a line cannot intersect quadratic many number of faces. It cannot. This area that it affects is linear, and the proof of this is by induction. And I think what it turns out is that it's linear, but it says probably at the end that it's bounded by 10m. So this says 5m here for the faces that are above, but for the faces that are below, it's also another 5m. So it's actually, if you have a lot of faces, this 10m is the same as like n log n, but it's linear, so it's constant. Whatever you have here, it's constant in front of it. So it's proof by induction. I'm not going to go into the details of this proof. As I said, we're just going to be using this proof as a way to bound our computational complexity by O(n) squared construction of arrangement of lines. Okay, so the algorithm just becomes this. If you look at the pseudocode, it's actually also here. To insert a line, what we are going to do is we are going to find the bounding box edge that our line intersects with. Okay, so when we are inserting it, so this is how the zone complexity is proven here. And the final thing is that we'll be able to construct it in optimal time and space O(n) squared. So let me actually show it here. Okay, at an intermediate step of the algorithm, where we have a bunch of lines already processed and inserted into the doubly connected edge list. Okay, now when I have a new line that I'm trying to process, this is what we do. For example, if I have a line that is like this, okay, what we do is we first, in O(n) time, there are many half edges that are on the boundary, right? Actually, all these clockwise twins, so these are the half edges of these faces, existing faces. I'm showing them counterclockwise, as you can see. This is the outer boundary of this face. And I have another clockwise, sorry, the other way. So this clockwise cycle of edges of the outside boundary is actually the boundary of the hole. So this box, bounding box, is like a hole in this unbounded face. There's an unbounded face in this subdivision that is outside. I'm not, also there's that single face because I'm not considering the parts of the lines that are outside the bounding box. Okay, so these parts here, I ignore them. So I treat my lines as if they are line segments within this bounding box. So there's a single unbounded face outside this bounding box because I'm only interested in the part of the line arrangement inside the bounding box. Therefore, these extensions of lines that are on the outside, I just ignore them. I don't care about them. Okay, actually I can directly erase them like this. Let me just get a very, so we can just erase them. Let me even get it larger. Okay, so we are not interested in these parts, which will now, we will have a nice single unbounded face outside. And what I'm trying to tell is that unbounded face has no outer boundary. There's no outer boundary cycle. If you remember the doubly connected edge list chapter, it doesn't have an outer boundary, and it will have one inner boundary, which is this hole, which is this bounding box we have here. Let's get back to the size 4. Okay, now if you look at the edges, half edges that are in this clockwise direction here, there are ON of them, and in ON step, what I will do is, given a line, so this line is the new line that I'm trying to intersect this doubly connected edge list with. The first thing is I find this entry point to my bounding box, and I find this entry point by intersecting my line with every one of those this whole inner boundary edges along the bounding box. Okay, this becomes my cycle of whole inner boundary here, and I intersect my line. This is Li, the ith line that I'm processing. I find the piercing point, the entry point to this bounding box. After I find this, it's associated with a face. This face is deleted and 2 new faces are inserted, F1 and F2. Okay, this edge here that I pierce through the entry point, it's also chopped into 2. Then by following the next pointers of this, I find the next, I find the next edge that I intersect with, it's this one. Then I will jump to this face. Then after that, I will jump to this face. So by following, as you can see, these edges, and by following the next pointers of them, I can traverse through this doubly connected edges, and all the faces that are affected by this will be modified. These faces will not be affected at all at this ith iteration, incremental iteration. And what we do is, as I said, we delete the original face record, we replace it with 2 new face records. Each of the faces that I intersect with they are doubled, and the half edge records are also changed. And this process, since the zone of a line is linear, this process is going to take OI time. If I'm in the ith iteration, I-1 lines have already inserted. It will take OI time to insert this ith line. If you sum all of them from 1 to n, you will get yourself your ON square complexity algorithm. After we have the zone, we are going to then compute the level. We are going to do it for all of the lines. And after we have the doubly connected edge list, the arrangement, the next and final step is to compute the level of each of the vertex in this doubly connected edge list. So what's the level? So let's go to that part next. And let's also quickly go over this pseudocode. So what it basically tells is that the first step is computing the bounding box by considering all of the vertices. So the first step takes ON square time. Second step is O1 time. We construct a bounding box with 8 half edges for each side. sorry, the bounding box is a rectangle of 4 edges. Each of those edges is two half edges with their twins, so there will be 8 edges in my initial doubly connected edge list in step 2, and I can construct it in all one time. And from steps 3 to step 7, this is the incremental step where I add every one of those lines one by one. The first step is finding the edge on the bounding box, that the leftmost intersection point. You can either you can keep the original bounding box edges without modifying them to actually optimize this step. Maybe you can keep pointers to the original edges whenever you divide them on your doubly connected edge list. You can still maintain the long edges of the 4 edges of the original edges of the bounding box could be kept at this point to find the edge that intersect the leftmost intersection point of your line. And then so this is the entry point. The first step 4 is finding the entry point. After you find the entry point, what you do is you start with that face F, and while you exit the bounding box, until you exit the bounding box, so steps 6 and 7 is the walk through the traversal in the doubly connected edge list by following the next and twin pointers of those edges. So we walk through from face to face, we walk along the doubly connected edge list until we exit to the unbounded face again. So steps 6 to 7 take ON time, linear time, or OI time. In the ith iteration, it will take OI time. So the total, it takes n squared time. So this is how we build ourselves an arrangement of lines. And the final thing in this chapter is, this is the thing that we try to compute. For all of the vertices in our arrangement, we want to associate them with integer values, which tells us how many lines are above this point. For example, look at 3. Where is this 3, this vertex? This line, and this line are above it. So there are 3 lines above it. Out of these, in this arrangement, there are 5 lines, right? So 3 of them are above it. This one. At this point, strictly 3 of them are above it. 2 of them are intersecting at this line. And one of them, here, this one is below it actually. So there are 6 of them. Yeah, there are six lines in this arrangement, not 5. I counted wrong. So 1, 2, 3, 4, 5, and 6. So there are 6 lines in this arrangement. Out of those 6 lines, 3 of them are strictly above it. And the lines that are above, let me just again copy this to GIMP and try to describe it over there. All right, so if you look at here, okay, this point is 3 because this 1, 2, 3, these 3 lines are strictly above this point. And when I come to this point, okay, and here, this area here, actually, any point at this point, for example, it was 3 here. Any point here, there are 3 lines strictly above this one. At this vertex, a line with a positive slope intersect this one, which tells me that for the region here, I mean, at this point, the level should increase to 4, but since I'm looking for strictly, because at that point there it's equal, it's on the line, but right epsilon towards the right, epsilon unit towards the right along this line, any point on this line will have a level of 4 because this new line, this is the 4th line that we have here. This new line that we intersected with points now, if you count how many lines are above the point that is here to the right of this vertex, we will count 4 of them. 1, 2, 3, 4. Okay, hence this part is 4. And here actually what happens is that for the parts that are here, it's 5, right? Because this line also has a slope of a positive slope. There are 4 lines strictly above this vertex, But if I had some points that are here along this region on this edge, the level of any point on this edge is 5. I count 5 lines that are strictly above a point on this edge, which are this is the 5th line. Okay, 1, 2, 3, 4, and 5. Okay, so from this 5, it's now reduces to 3 at this point. Why? Because these two lines that intersect at this vertex, they have negative slope. So what happens in this case is that, so when they have negative slope, if you're going to decrease that number, you decrease them immediately at this vertex to 3. Two lines with negative slope intersect me at this vertex, so 5 minus 2 is I have 3. Because at this point, since these lines are on the point, in this region, there will be any point on this edge will have a level of 3. There are exactly 3 lines that are above it. Which are those lines? 1, 2, and 3. These are the 3 lines that are above these points. Okay, so when we try to in other words, it's like this. The rule is like this. When we need to decrement due to a negative slope line intersecting at that point, we decrement exactly at that point. The decrement is done at that point because we are counting the number of lines that are strictly above a vertex. So equalities count towards the decreasing. I mean, at an intersection point, we need to decrease. If it's either going to stay the same like this, 3 stays as 3 here at this point. For example, if I have another vertex that was 3 here, it doesn't become 4 when I'm going to increase it like this. The increases affect the next vertex, but the decrease in the level is affected at that exact vertex. But the thing that you see here is that in O1 time, at every vertex, we can find whether we are going to increase or decrease how many times depending on the slopes of the lines that we intersect at that point. And we have this information in the doubly connected edge list. So this is what how we are going to compute the levels. Let me get back to the original figure. So what we are going to do is this. This is the algorithm. For each one of those lines, for example, when I'm processing this line in the first step, let's assume I'm processing this line. For this first vertex, I'm going to spend n time to count one by one how many lines are above it. So I'm going to find 1, 2, 3. 3 of them are strictly above it. This one, for example, is below it, so I don't count this line. So after I find this number, I set the level of this first vertex to be 3. Then again, I walk through since I have the doubly connected edge list now, I walk through the vertices again and by using the doubly connected edge list pointers in them, next to and by jumping to the next phase, I follow along these vertices. And at these vertices, either I'm going to increment the count or decrement the count, but each of them, I do it in O1 time. Okay? And there may be On of them in total. So the total process of finding the levels of the remaining vertices takes a total of On time. So On plus On, the first vertex took On time. All of the remaining vertices in total take On time, so which gives me On time complexity for a single line. I do it for all of the lines in my input, in my arrangement, which will result in an On squared complexity finally. So given a doubly connected edge list like this, an arrangement of n lines, I can compute the levels, how many lines are above each of these vertices. Each of these On squared vertices, I can compute how many lines are above them in total On squared time, which means that in my original space, I can compute for every one of those On squared lines that pass through all pairs of points. I can compute how many points are below them or above them in On squared time. So since I'm counting here the lines that are above, it will translate to how many points are below these lines in the original space. And this is what I wanted to compute actually. All right, so And so this means we can compute the discrete measure for our original problem in O(n) squared time in total, and the discrepancy can be computed in O(n) squared time. The maximum discrepancy can be found in O(n) squared time in total. Okay, so this concludes this chapter. The thing that I mentioned at the beginning of the second hour, another problem that we can solve by duality, I'm going to now describe that one. Do you have any questions about this arrangement of lines, the original problem, duality? Any questions, comments? You can write in the chat box. All right, I hope everything is clear. Now I'm going to talk about a different problem. Here the problem is like this. It's like a machine learning problem, classification problem, but in just 2 dimensions. It's basically a geometric problem, but it looks like a machine learning problem. We are given a set of points on the 2D plane, actually 2 sets of points. One of those point sets is, let's call them green points. The other point set is red points. So this is a different problem, okay? So this is a different example I want to show you to demonstrate how duality can be helpful to us. So look at these 2 sets of points. In machine learning, sometimes we ask whether a given 2 sets of classes are linearly separable. In other words, we ask this question: is there a line that we can draw so that all of the green points are one side, all of the red points are on the other side? Sometimes this may not be possible, and we just accept to make certain errors. Okay, we try to minimize the number of errors we make. But in this purely geometric version of the problem, I ask this question. I give you 2 separate sets of points, and I ask you this: is there a line that separates these 2 points? Can you draw a line in between them so that all of the points of one set is going to be on one side, the other set is going to be on the other side? So how are you going to solve this problem? One solution may be to use the convexals, right? You can, when I ask this question to students, most of them answer we can compute the convexal of the green points. Okay, and we can compute the convexal of the red points. And by checking the convexals, if they're not intersecting, they may be linearly separable. Or if, in order to draw the line, we can look at the tangents of these convexals. But basically, you reduce the problem to a convexal, 2 convexals problem, which then you can find in linear time, in constant time, whether these 2 are intersecting or not, or whether there's a line that passes between these 2 convexals. But this will have a complexity O(n) log n, right? If you have a your total number of points as O(n), you will have an n log n solution, which is not bad actually. N log n is a very efficient algorithm. We have n points. Now, what if I tell you that? I'm not tell you, but ask you, is it possible to solve this problem in O(n) time? I give you n points in total in 2 sets, green points, red points, and I ask you to find me whether there is a separating line, whether these 2 sets are linearly separable in linear time. Okay, what is your... now you should actually be thinking about the duality, right? Where does duality help me in this case? Because this seems like a completely new problem, right? We haven't talked about this problem in this class at all, or did we? So this is, maybe we have talked about this exact same problem, but maybe not in this world, not in this, maybe in some parallel universe we have talked about this, in the dual universe. Let me give you another hint. Is it possible to find the linear separation of these 2 points in expected ON time. Okay, expected ON time. So this is a big hint. So what kind of an algorithm you can use to find whether these 2 points are separable in expected ON time? Any suggestions? You can write in the chat box if you have found the solution, or maybe it's too obvious that you don't write the solution. But let me just talk about the solution here. In the dual space, so what we are looking for is a line in such a way that all the green points are below the line and all the red points are above the line. Okay, so here this is what linear separable means. I mean, if I can draw a line such that all the green points are below it and all the red points are above it, then such a line exists. So I'm looking for a line, and there are infinitely many lines that. So this seems like our solution space is infinite. But what we can do is this. Now, what if all those green points or red points in the dual space, all of them will be lines, right? They will be lines, and I will have green lines in the dual space. Now, what I'm looking for in this dual space is a point. Now, I will be looking for a point in such a way that that point is below all of the red lines and above all of the green lines, or vice versa. I may have confused, but in any case, I want a point that is above all of one set of lines and below all the other set of lines. So this above-below relationship, does it ring a bell? I mean, I'm looking for points that are below. What does this, each of the line, what does it tell me? It says that you're looking for a point in this half space. This other line says you're looking for a point in this half space. And this one saying you're looking for a point in this half space. And this red one, green one saying you're looking for a point in this half space. So each of them is telling me a half space to search for. So what is this? Intersection of half spaces, half planes. And I'm looking for an, so in other words, this is chapter, the 2D linear programming problem. It becomes the dual problem of this first problem, which seemed like a different problem that we haven't seen before. In the dual space, it's exactly becomes like the 2D linear program. Our points in the original space, now they become lines, and we're looking for a point in a certain region of the space for each of these lines. We're looking for a point. So if these half space intersect, if the half spaces intersect, it becomes exactly the same problem as the kernel problem in the midterm exam, the fourth question, whether a polygon is star-shaped or not. You apply the same algorithm here. If the intersection of these half planes is not empty, then they are linearly separable, and you can choose any point. By the way, there may be multiple solutions. For example, this line also linearly separates. This line also linearly separates. Look at all these lines. They all linearly separate these two things. So you can choose any one of these lines, same as here. If the intersection of these half spaces is non-empty, then it means that they are linearly separable, and you can use this randomized incremental solution with expected ON time to solve this problem. All right, so this is how we can apply, how duality helps. The dual transform turns it into a problem that we already knew how to solve, and this is some new technique that will help in the computational geometry problems. Not always, dual transforms are not always good. Sometimes they may help, sometimes not. But just trying it and trying to look at the problem from a different perspective, obviously, is something that we should try. Okay, so that's it for this week. If you don't have any other questions, I will stop the recording and finish the lecture today. And in the remaining weeks, we will talk about, in the next week, we are going to talk about two new data structures, interval trees and segment trees. And in the final 2 weeks, we are going to talk about robot motion planning, the Minkowski sum problem, and visibility graphs. All right, so that's it for today. See you all next Wednesday. İyi günler. Take care. Have a good rest of the week and have a good weekend. Let me stop.